Welcome to Lecture 17. We'll be covering aircraft requirements. Some of them are covered in the book. So, to achieve an acceptable safety risk target of 10 to the minus 7 fatal accidents per flight hour, certification is an important aspect of aircraft certification. Actual risk is typically less than 10 to the minus 6 flight per flight hour and is higher for rotorcrafts or private aircrafts. And this is equivalent to one fatality for maybe plus minus 3,300 millions of seat kilometers. If you look at comparisons against a bus, is 1.3 times higher. The train is 3.3 times higher. A car is 13.3 times higher, which is more risky. Motorbikes even higher, 323.3 times higher than the risk for an aircraft. Airworthiness authorities prepare further standards, regulate, check, approve, control, and sanction. Minimum requirements imposed by the International Civil are imposed by the International Civil Aviation Organization. The European Aviation Safety Agency regulates specifications in Europe and publishes the certification specifications, CS. The Federal Aviation Administration, FAA, prepares the Federal Aviation Regulations, FAR, and they usually come along with advisory circulars that provide additional information about how to comply with the regulations. The application letter for certification steps incorporates preliminary data like drawings, performances by the manufacturer, and the definition of the certification basis by the airworthiness authorities needs to be looked at. So, for example, it includes special conditions for unusual or novel or reputed unsafe designs, demonstration of the compliance by the manufacturer, and acceptance by type certificate. So, these are the things that go into the certification steps of an aircraft. Application letter usually incorporates preliminary data, like I said, and it defines the certification basis. I covered this already, but major types of requirements concerning the aircraft, you have to look at static strength, which is a resistance to exceptional events, endurance, which includes fatigue and damage tolerant designs. They have to show resistance of the aircraft structure against any damage induced during the service life. You also have accidental hazards like lightning strikes, bird impact, fast decompression, and fire resistance. And then you have other types of things that need to be looked at, like emergency landing, flutter, quality control. Compliance to these requirements are usually proven by tests with calculations. These tests can be quite expensive, but they need to go along with analysis, like we've discussed several times. Aircraft certification tests typically include cruise and climb performance tests, flutter tests, which are really to analyze the vibratory behavior of the aircraft structure throughout the whole flight envelope. The structure has to adequately be damped in order to avoid flutter, as dangerous undamped vibration modes can caused by aerodynamic structural response coupling. So you want to make sure you don't have this aerodynamic structural response coupling, which, for example, will take the wing and break it apart, or any of the control surfaces. The minimum unstick speed test needs to be performed. It's to validate the minimum takeoff speed at maximum pitch angle. Cold soak and hot high test needs to prove functionality under extreme weather conditions, where, for example, you're going to Alaska or very cold conditions like North Russia. Those areas we need to make sure that these aircraft can do a good job at hot and cold conditions. For example, landing at very hot conditions or taking off at hot conditions. Auto land test to make sure that the aircraft can survive poor visibility conditions like landing and rollout operations. You want to make sure you can do that with autopilot. You also have to do a water ingestion test because you could be flying over rain. We want to make sure the engine can do a good job there. Acoustic testing, like noise pollution, and then lightning strike test. There's other tests too, like for example, taking a blade and breaking it apart to see if it can survive, and many other tests. There are structural tests in nature, like pulling a wing and pushing, fuselage testing, pressurizing the fuselage, and things like that. Structural tests include reaction of structures facing loads met during their lifetime. You also want to perform some of these tests on non-flyable airframes by hydraulic actuators. Many other tests are also performed on smaller subcomponent level parts like valves, piping, and things like that. There are two kinds of tests. I already covered some of them verbally, but you have the static test and the fatigue damage test. The static test is looking at the behavior of the structure under normal and exceptional loading conditions encountered during flight conditions. And in this static test, you're looking at limit load conditions, ultimate load conditions, and the breaking point, which is the point at which failure could occur. And it has to occur above the ultimate load level. The fatigue and damage test, right there, what we're looking there is structural response to repeated operation conditions over the lifetime, simulating a large number of cycles, and that will include taxiing, takeoff, cruising, and landing. And like I said many times before, the building block approach is necessary to ensure success during the test campaign. Here we're looking at small coupon level tests, subcomponent level tests, and larger component tests, all the way to the full scale test. And what we want to make sure is the analysis can match the testing at every step of the way to increase the confidence in the design. Structural testing, we'll be covering a lot about this Venn diagram. I'll be talking about this velocity, the airspeed versus the load factor. We'll be talking about that. But we want to make sure that the structure can resist critical loads that can be encountered during the life of the aircraft. And the Venn diagram, which I'll be discussing later, really provides an envelope to ensure that we're testing all the corners of this envelope. Design load factors are basically really discussing the European standards, also the FAA the FAR regulations, United States. The limit load factor and limit, here you can see here in this coder, is the maximum expected load during service, and that's this point right here, and that'll envelope any gust, any ground loads, and the plane at these limit load conditions when you apply the loading cannot experience any permanent deformations. So, but above limit loads, permanent deformations could be acceptable. We want to make sure that the ultimate load, the factor is typically 1.5 from end limit to end ultimate. And here, the structure can experience permanent deformations. We want to make sure that a factor of safety of 1.5 is applied, and the structure has to withstand ultimate load for at least 3 seconds without failure. So if I have a wing that's going to say 100,000 pounds, I need to make sure that wing can survive 150,000 pounds for 3 seconds. And you cannot have any permanent deformations below 1.0 limit load, but you could see some above 1.0. The rules for fatigue and damage tolerance are covered in the CS 25.571. An evaluation of the strength, detail, design, and fabrication must show that catastrophic failure due to fatigue, corrosion, manufacturing defects, or accidental damage will be avoided throughout the operational life of the airplane. So, in case of damage, catastrophic failure has to be avoided. The remaining structure must be able to resist the reasonable loads until damage is detected. And we also have to make sure that we can withstand large damage in the structure and that the structure can land successfully even without damage. The three main sources of damage, we covered a lot of these many times, but it's worth repeating, could be in corrosion, aging, fatigue, and accidental issues like bird strike and lightning strike. Even when I have these kind of damages, I should be able to land the structure successfully. And we have to make sure we can. Otherwise, catastrophic failure events could happen. Corrosion is something we've talked about, is metals in contact with organic matrix of composites, and you could have rusting by galvanic corrosion. We talked about that. You can insulate the materials in between to make sure that doesn't happen. Aging, like humidity, Degradation of composites can occur due to moisture. We covered this extensively, and you could have even thermal conditions affecting the composites. The damage tolerant design for metals, usually what it does, it assumes a crack or defects are present, and they come from either manufacturing, corrosion, fatigue, impact damage. You're looking at how tolerant the design is, and you want to characterize the crack evolution as its effects on the structure. You want to make sure that these damages will not lead to a catastrophic event. Using this information, you need to plan for inspection intervals. Periodic inspections are implemented every many months or every many flights to check for how the flaws has progressed. Then that's going to help you then determine whether you need to remove the structure out of service or repair the old structure from service before the predicted end life, or it may show that no damage has grown so you can continue to extend the life of the part. There could be possible that the fatigue of the metals are stable and that things are okay. But you don't know that until you inspect every so often. Damage tolerant design for composites is less of an issue than metals. You're gonna have, well, impact damage can be an issue, but uh, fatigue is not as big of a concern with composites typically. But delaminations can be an issue, and so you can do a lot of testing to gain confidence that you don't have a fatigue concern. Delamination phases are exposed to additional degradation associated with environments, and the idea here is to apply the no growth concept. And the way you do that is that you limit the strains in the structure. And by limiting the strains fairly low, you can then guarantee that the strains are so low that delamination growth is unlikely. But typically, you want to prove that out through testing of subcomponent level tests using similar processing and similar um, type of testing then and also similar manufacturing and materials. So what does the test program look like? You have the durability demonstration, which is the demonstration of a fatigue safe life, flaw tolerant safe life design. And usually the life is enhanced by a scatter factor and it is equivalent to crack free life. So no fatigue crack initiation. And so in this case, you have the test right here. You want to make sure that your fine elements verifying that structure. And you want to come up with a structure that has a minimum quality. That's what you want. You want whatever quality you're going to allow, you want the minimum quality they're going to allow. And that's what you want to manufacture here. And so in this test, what you're really looking at is ensuring that you do a safe life demonstration. Now, this safe life demonstration is going to be a pristine one. So again, here's the difference between safe life in the aircraft style and the launch vehicle style. So here again, no fatigue crack initiation at the end of this testing. Ultimate load test at that point. And here, what you're looking for is demonstration of the residual strength with worst case environmental conditions after the fatigue test. So after you're done with the fatigue test, ultimate load test, and you have to meet the 1.5. Then you have the damage tolerance evaluation, which is to demonstrate no growth, and that means an accidental damage is induced, reduces the ultimate strength capability, but it will be okay below limit loads. No subsequent damage growth occurs during that one inspection interval. So that's what you don't want that. And then you want to demonstrate residual strength to a level lower than ultimate load, but still above limit load. The FAR regulations that covered some of the European approaches, but now let's look at the FAR regulations. 25.613 covers the statistical basis, their environmental effects, and then in terms of the Mill Handbook 17, the same CMH 17, Composite Materials Handbook 17. Then 25.615 covers the design properties. All these can be found online very easily. A basis for single load path, B basis for redundant structure. We already covered that. Then you have the advisory circulars 20107A. Then you have 25.613, 25.615, and 25.6.03 similar to FAR regulations. Then you have the FAR 25.603 materials, which will cover the suitability and durability established by test, conforming to specifications that ensure the strength and takes into account the environmental conditions. 25.605 covers the fabrication methods. Fabrication methods must produce consistently sound structure, and new methods must be substantiated by test. FAR 25.609 talks about how to protect the structure against deterioration or loss of strength. FAA AC Advisory Circular 2107A talks about the composite aircraft structure and presents an acceptable but not the only way to certify an advanced composite structure. The Advisory Circular 2126 covers the quality control for manufacturing composites and presents an acceptable means for complying with the quality control requirements in FAR 21. And all this can be found online. You can download all this data. And then you have the ACG 25.603, which is composite aircraft structure, which is similar to this advisory circular. Part 25 airworthiness standards, transport category airplanes. So that's, we're looking at here, transport category airplanes, um, talks about loads, for example. And for loads, we're looking at strength requirements are specified in terms of limit loads. We cover that to the maximum loads to be expected in service. And then you have the ultimate loads, which are the limit loads multiplied by prescribed factors of safety. Unless it's otherwise provided, the prescribed loads are the limit loads. B, unless otherwise provided, you're going to have to specify um, specified air, ground, and water loads must be placed in equilibrium with inertial forces, considering each item of mass in the airplane. These loads must be distributed to conservatively approximate or closely represent actual flight conditions. Methods used to determine load intensity and distribution must be validated by flight load measurements unless the methods used for determining those loads conditions are shown to be reliable. In other words, you want to apply the loads as close as possible to what is going to experience in flight. And those where analysis can be very valuable to show that you are in line there. If deflections on the loads will significantly change the distribution of external or internal loads, this redistribution must be taken into account. In other words, if there's large deformations, the loads can then change the distribution, so you have to account for that somehow in the test. Part 25 airworthiness standards. Now I go to the safety factor. It talks about 1.5 must be applied to the prescribed limit load, which are considered external loads on the structure. When a load condition is prescribed in terms of ultimate loads, a factor safety need not to be applied unless otherwise specified. In other words, if the ultimate loads already include this factor safety, you don't have to worry about it. But the bottom line is the factor safety is 1.5. That's what he's telling us here. Strength and deformation. The structure must be able to support limit loads without detrimental permanent deformation. I covered that in the European standard, but just conforming, still conforming here with the the FAA regulation. At any load up to limit loads, we cannot have deformations of the structure to interfere with the safe operation. In other words, at limit loads, the structure has to be functional. And then you have to show that ultimate loads, there's no failure for at least 3 seconds, again, consistent to European standard. However, when the proof strength is shown by dynamic testing to simulate actual load conditions, the 3 second limit does not apply. Static tests conducted to ultimate loads must include the ultimate deflections and ultimate deformations induced by the loading. And when analytical methods are used to show compliance with ultimate load strength requirements, it must be shown. So if you're going to use analytical methods, you have to show the effects of deformation are not significant, the deformations involved are fully accounted for in the analysis, or the methods and assumptions used are sufficient to cover the effects of these deformations. Again, very important here, quite consistent to the European standard. And here we have that we need to show that where structural flexibility is such that any rate of load application likely to occur in the operating conditions might produce transient stresses appreciably higher than those corresponding to static loads. The effects of this rate application must be considered. So anytime the rate of load application can be problematic, we have to show those effects. The airplane has to be designed to withstand any vibration and buffeting that might occur in any likely operating condition up to the diving speed. We'll cover that later, including stall and probable inadvertent excursions beyond the boundaries of the Buffett onset envelope. We'll talk about this a little bit later. This must be shown by analysis, flight tests, or other tests found necessary by the administrator. Unless shown to be extremely improbable, the airplane must be designed to withstand any forced structural vibration resulting from any failure, malfunction, or adverse condition in the flight control system. These must be considered limit loads and must be investigated at airspeeds up to the cruising. That's the cruising speed right here. Proof of the structure. Compliance with strength and deformation requirements of this subpart must be shown for each critical loading condition. Structure analysis may be used only if structure conforms to that for which experience has shown this method to be reliable. In other cases, substantiating tests must be made to load levels that are sufficient to verify structural behavior up to the load specified in 25.305. So again, that's what proof structure is. You have to show that the structure will be okay. When static or dynamic tests are used to show compliance of these requirements for flight structure, appropriate you have to appropriately correct the loads for the correction factors. And that means the test like flight differences that we talked about. Maneuvering conditions like symmetric and flight maneuvering envelopes need to be considered. The strength requirements must be met at each combination of airspeed and load factor. And we want to make sure that we're fully encompassing the VN diagram that we talked about. And we'll be talking about that later. That's the speed load factor diagram that we talked about. Okay, very important consideration that I don't want you to forget. Okay, and so we also have to make sure that uh, we fully encompass it, the Venn diagram, but we want to make sure it's reasonable. We then have to look at design speeds. We have to be good to the design speed. That means cruising dive speed, design maneuvering speed, and designing for maximum gust intensity. We want to also make sure that we are looking at the limit maneuvering load factors. So here it says whenever, except we're limited by static lift coefficients, and we'll be talking about lift coefficients, the airplane is assumed to be subjected to symmetrical maneuvers resulting in limit maneuvering load factors prescribed in this section. Pitch and velocities appropriate to the corresponding pull-up and steady turn maneuvers must be taken into account. The positive limit maneuvering load factor N for the load factor is N for any speed up to Vn may not be less than 2.1 plus 24,000 divided by the weight plus 10,000. Except for that, the load factor may not be less than 2.5 and may not be greater than 3.5, where W is the design maximum takeoff weight. We'll be talking a little bit more when we talk about the Vn diagram, but just keep in mind that there's a limit to maneuvering load factors. The negative limit maneuvering load factor may not be less than 1 at speeds up to the cruising velocity and must vary linearly with speed from the cruising velocity to 0 at the diving speed. Maneuvering load factors lower than those specified in this section may be used if the airplane has design features that make it impossible to exceed these values. So we have to really make sure that we're staying within the limits of the VN diagram, and then we're making sure we're not going above the limit maneuvering load factors. Gusts and turbulence have to be taken into account. I'll be talking about the criteria for that. The airplane is assumed to be subjected to symmetrical, vertical, and lateral gusts in level flight. Limit gust loads must be determined in accordance with the provisions that follow. Loads on each part of the structure must be determined by dynamic analysis, and the analysis has to account for the unsteady dynamic characteristics and all significant structural degrees of freedom, including rigid body motions. The shape of the gust is given in the document. I'll show it to you later in the next lecture. You also have to make sure that you're accounting for design fuel and oil loads. And that means sloshing, for example, that can account for sloshing. The disposable load combination must include each fuel and oil load in the range from zero fuel and oil to the selected maximum fuel and oil load. A structural reserve fuel condition not exceeding 45 minutes of fuel under the operating conditions here is applicable and may be selected. If a structural reserve fuel condition is selected, it must be used as a minimum fuel weight condition for showing compliance with the flight load requirements as prescribed in this subpart. The structure must be designed for a condition of zero fuel and oil in the wing at limit loads corresponding to a maneuver load factor of 2.25 and gust conditions in these sections. But assuming 85% of the gust velocity is prescribed here and 85% of the turbulent intensity is prescribed here. Fatigue evaluation of the structure must account for any increase in operating stresses resulting from the design operations, and flutter deformation and vibration requirements must also be met with zero fuel. Again, you have to meet the zero fuel conditions as shown here. The fatigue evaluation has to be conducted, and I already covered a lot of this, and so I don't want to repeat it again, but you want to make sure you implement inspection thresholds for the following types of structures based on crack growth analyses, assuming that the structure contains an initial flaw and is of the maximum probable size. And that's going to be related to the manufacturing process. So that's a very important consideration. You have to identify the principal structural elements and design detailed design points for which the failure of those components could cause catastrophic failure of the structure. So again, need to make sure that you have identified every single point failure that could cause catastrophic failure. You also need to define the load spectra, the temperatures, humidity, humidities expected in the service life, because that can play a role in that test program. And so again, you want to make sure you're designing against catastrophic failure due to corrosion, manufacturing defects, accidental damage like impact damage, lightning strike, and you need to account for all of that. The airplane must be protected against catastrophic effects from lightning. We talked about that earlier. We want to make sure that you want to design the components so that the strike will not endanger the airplane. And you want to make sure that for non-metallic components, you want to design the components to minimize the effects of strike and making sure that you can divert the electrical current in a way that you're not endangering the passengers. Other consideration, no airplane may be operating beyond a number of cycles equal to half the number of cycles accumulated in the fatigue test article. Now, this looks different from the launch vehicle philosophy, which is 4x, but here you're also doing inspections quite a bit and your analysis is a little more conservative. The residual strength evaluation must also show that the remaining structure is able to withstand loads corresponding to several conditions: fatigue safe life evaluation, sonic scatter fatigue, and impact damage evaluation, like bird strike. There are other considerations in FAR 25 that need to be accounted for, like high lift devices, rolling conditions, yaw maneuvers, engine failure loads, which combine 1G flight loads with the most critical transient dynamic loads and vibrations. And that's determined by dynamic analyses. That can include failure of a blade, shaft, bearing, or some sort of bird strike event. Any permanent deformation from these ultimate loads must not prevent continued safe flight and landing. Very important. Side loads, gyroscopic loads, unsymmetric loads due to engine failure, speed control devices, control surface and system loads, ground gust conditions, taxi takeoff and landing, and towing loads in the emergency landing. All this is considered in FAR 25 and needs to be looked at. Pressurized compartment loads need to be looked at. The airplane has to be strong enough to withstand the flight loads combined with pressure differential loads from zero up to the maximum relief valve setting. The external pressure in flight and stress concentrations and fatigue have to be accounted for, like those from a window. If landings may be made with the compartment pressurized, landing loads must be combined with the pressure loads. That makes sense. You want to combine all the loads to get the worst case scenario. The airplane must be designed to withstand the pressure differential loads corresponding to the maximum relief valve setting multiplied by a factor of 1.33 for airplanes to be approved up to 45,000 feet, or by a factor of 1.67 for airplanes to be approved above 45,000 feet. Any structure, component, or part inside or outside of a pressurized component, the failure which could interfere with continuous safe flight and landing must be designed to withstand the effects of sudden release of pressure through an opening in any compartment, that's the fuselage, in any compartment at any operating altitude resulting from each of the following conditions. Penetration of compartment by portion of an engine, so you have a blade cracking and then it hits and punches the fuselage. You need to survive that. You don't want an explosion that causes the whole airplane to come down. Unsymmetric loads due to turbine failure need to be looked at carefully. And I'll let you pause the video and look at this carefully, but you want to make sure that the timing and magnitude of the probable pilot corrective action must be conservatively established. And you want to make sure the time history of the thrust decay and drag buildup occurring as a result of prescribed engine failures must be substantiated. And you want to make sure that you can land, and that's the whole point of this. You want to make sure you can land, and so I'll let you pause the video and read through this here, section 23.367. Here we have a number specification for bird strike, and that's covered in parts 23, 25, 29, and 91. You're looking at wings, body, and windscreen windows. The airplane has to be capable of successfully completing a flight during which likely structural damage occurs as a result of impact with a 4-pound bird when a velocity of the airplane relative to the bird along the airplane flight path is equal to the cruising velocity at sea level, or 0.85 cruising velocity at 8,000 feet, whichever is more critical. The empennage of the structure has to be designed to assure capability of continued safe flight and landing of the airplane after impact with an 8-pound bird when the velocity of the airplane is equal to cruising velocities at sea level. So this is very important. Some of this is done through testing, and then military has their own specifications. I'll let you pause the video and read that. For military, you're looking at for no penetration of cockpit. You're looking at no penetration of fuel tanks because of potential fire hazard and no damage to control surfaces. Those are the main specs. Durability for engines, you want to make sure that the engine and design and construction must minimize the development of an unsafe condition of the engine between overhaul periods. The design of the compressor and turbine rotor cases must provide for the containment of the damage from a rotor blade. And there is a YouTube video you can watch where a blade is being broken on purpose to see if the engine can sustain that. Energy levels and trajectories of fragments resulting from rotor blade failure that lie outside the compressor and turbine rotor cases must be defined. Each component of the propeller blade pitch control system, which is part of the engine type, must be designed according to this section. So I'll let you pause the video and download this so you can read more. You also have a number of specifications on the pressurized engine static parts. And that means that any component that's pressurized, that has gas or liquid pressure loads, have to be stabilized at least for 1 minute. You have to show good. And you have to make sure there's no permanent deformation beyond service limits or exhibit leakage that could create a hazardous condition. You're looking at 1.1 times the maximum working pressure, 1.33 times the normal working pressure, and then you also want to make sure uh, that you don't want to have exhibit fracture burst when subjected to the greater of the following pressures: 1.15 times the maximum possible pressure, 1.5 times the maximum working pressure. So this one here is for leakage and permanent distortion, and this one here is for fracture or burst. And so here you have also a number of other requirements that need to be looked at. Sometimes fracture analysis is also performed to make sure you have a good design. You're also looking at foreign object injection like ice. You want to make sure that ice will not blow up their aircraft, the engine. Ingestion of ice under conditions of these sections may not cause immediate or ultimate unacceptable sustained power or thrust loss or require the engine to be shut down. For an engine that incorporates a protection device, compliance with this section need not to be demonstrated with respect to ice formed forward of the protection device if it's shown that the ice is of a size that will not pass through the protected device. In other words, you have a way of containing the ice, and the ice is stopped by the protecting device. You also have to look at requirements relative to ice, and here there's a table that looks into that. for ice ingestion. I recommend that you pause the video here, read this, and then pause the video here, and then read this, so you can kind of see the, the the types of ice that we're looking at, the geometric characteristics. You also have engine requirements for endurance testing. You have to show that um, the engine can operate for a number of hours operation. Again, you're going to have inspection intervals as well, but you want to make sure you can pass this endurance test, which are quite severe. And I invite you to pause the video and read them. So with that said, I'll conclude the fire regulations and the European standards. There's many other regulations, but I think these are the key ones, and I think you do have the time um, to kind of go and download some of these requirements. Here I mentioned the top level view in FAR 25, which you can download, read, and get acquainted to what's in there. I also recommend for you to pause the video and download these documents here. These FAR regulations and advisory circulars can be of great value to really understand what the implementation looks like. With that said, I hope you have a good day.